My name is Adam, and together with Szymon, we will show you a few techniques that you can use to perform well on natural language processing tasks when lacking labeled data. So here is the presentation outline. So I will very quickly do a short introduction to natural language processing. Then I will introduce a couple of models for NLP that will be used in the last part of this talk. And I will finish with showing you what was our motivation for tackling those problems. And then Szymon will show you the meaty part, will present you different techniques that you can use to deal with the problems, and also some experimental results. All right, so NLP technologies are present everywhere these days. So, for example, you have a couple of examples here. So they are, for example, used in chatbots or voice bots, in personal assistants like Siri or Google Assistant. They're used in translators, for example, in Google Translators, in search engines like Google, like Russian Yandex or Chinese Baidu. They're also used for automated document processing and, for example, for text generation, for example, for fake news generation. And of course, natural language processing consists of many different problems which can be roughly divided into three categories. And the first category are just basic classification problems where you have text as the input, and you want to predict a class label or labels when you're solving, let's say, multi-label classification. And here we have two examples of such problems. The first one is sentiment analysis. So here, basically, you would like to predict what is the sentiment of a particular statement. And the other one is intent analysis. So here you want to predict what was the intent of the author of the statement. The other group, the next group, is where rather than classifying the text as a whole, you want to classify each word as in the text individually. And here are two examples of such problems. The first one is named entity recognition. So basically, you use these techniques if you want to extract some useful information from the text, and you are classifying each word in the text. So, for example, you can classify that this word refers to a person, to an address, to date, and so on. The other one is reference resolution. So here, rather than here we are just classifying. You want to find the words that refer to the same object, for example, to the same person. So in this example, you have, for example, Paul Allen, and it gets label 0. Then you have Alan, he, Paul. All these 5 words refer to the same person. So this is the idea here. And finally, the last group of the problems are basically text-to-text problems, where you have text as the input and also you have text as the output. And here you have also 2 examples. So for example, machine translation is that kind of problem. So you have an input in one language, and you would like to generate an output in the other language. The other example is text summarization. So you have long text as the output, and you would like to generate a short summary, short abstract as the output. All right, so of course right now, deep learning is state of the art for most of, or maybe for all even NLP problems. And this is what the typical deep learning NLP pipeline looks like. So basically you have a raw text as the input, and then you have 3 consecutive steps. The first step is called tokenization. Tokenization is basically just replacing the raw text into chunks of text. And basically those chunks can be just words or or maybe word parts. So here is the example of such tokens. And there are several techniques that you can use here. So for example, you can use byte per encoding, word piece, universal language model on sentence piece. I think these four are the most popular at the moment. And then the next step is changing the tokens into real valued representations. So basically, you can use there some very basic methods. It's called neural embeddings. Or you can use some more sophisticated methods, more powerful language models, like, for example, BERT, XLNet, or GP2. And the last step is just modeling part. So you are just training a task-specific model. And depending on how powerful model you are using in the second step, for example, if you are using just such a powerful model as BERT, you can use only a linear layer to perform the final, for example, classification. If you are using something more simple, like, for example, word-to-vec, GLOF, or fast text, you can use then more powerful model here. So, for example, recurrent neural networks or transformers. For those of you who are not familiar with neural embeddings, this is just a very, very general idea of what it is. And so basically, neural embeddings is just putting the words into the Euclidean space in such a way that words that have similar meaning or appear in similar contexts will lie close to each other in this space. So for example, here you can see that there are some kitchen equipment here. So for example, oven, refrigerator, microwave. So probably these words appear in the similar context in the text. So they have similar, in this case, two-dimensional real-valued representation. And one of the techniques that you can use for generating such embeddings is fast text. You can visit the project webpage, and there you can download, I think, embeddings for almost every language, including Polish, of course. So I recommend you to try this. And then, moving to the modeling part, probably you're all familiar with recurrent neural networks. So these are the equations for the very basic recurrent neural network. And actually, such networks suffer from a phenomenon called vanishing gradient problem. And this causes that this vanilla recurrent neural network actually are not capable for capturing longer-term dependencies, which is basically crucial when we are modeling textual data. So rather than using vanilla recurrent neural networks, we are using techniques like long short-term memories or gated recurrent units because they do not suffer from vanishing gradient problem, and basically they are able to capture longer-term dependencies. And using such LSTMs, for example, you can build very powerful end-to-end models for text-to-text problems, like, for example, sequence-to-sequence model. And the idea here is that you are taking a raw text as the input, and you are processing it with the encoder part. Here you have a latent representation for the input, and then you are using the decoder part to generate the output. And the problem with LSTMs is that they are not good in parallelization. So you cannot train them efficiently, and training is usually very, very slow. And more or less 2 years ago, a paper called Attention is All You Need came out, and this was actually a game changer in the field, because what they proposed in the paper is also an encoder-decoder and architecture for solving text-to-text problems, but rather than using recurrence for modeling textual data, they are using something that is called self-attention mechanism. And such model can be actually can be very easily parallelized during the training, and because of that you can build much deeper architectures and train them. And this was actually this opened many new directions in NLP. And here we have just a very, very basic idea what self-attention is. So the idea is that you have words as the input, and each word is represented by its embedding, and then you would like to process it using the self-attention mechanism. So basically you are just calculating a new embedding for each word, which is a weighted sum of the embeddings of all words, and the weights are calculating using the attention mechanism. It works more or less like that, that for each word you are calculating query, key, and value. This is based on 3 different linear transformation of the input embedding. And then you are calculating the dot product between each pair of query and key. And based on those dot products, you are just calculating the attention vector, and based on that vector you are just taking the product of the attention and values, and this is how you are calculating the new embedding. And actually transformers are now building blocks for many famous NLP architectures, like BERT, for example. And BERT is nothing more than just a deep model that is built from stacked transformer encoders. And this is actually a multitask model, so you can use it, you can fine-tune it for to many different tasks, for example, to classification problem, to named entity recognition problem, to question answering problem. And BERT is trained in self-supervised manner, so you're first just training this deep architecture without using any labels, and then you're just fine-tuning it to your specific task. What is maybe worth mentioning is that BERT itself can be used as a feature extractor for textual data. So you can take a text as the input, process it using BERT, and then you have representations. Basically, you have features for each word, and then you can just process it further with some other model. And this is the model that we will be using in the rest of this talk. This is something else than BERT. This is our idea how we can combine transformers to make them suitable for very long documents. So our idea is that we want to, for example, classify very long documents. And the idea here is that you are building hierarchy of transformers. So in the first step of this hierarchy, you have word-level transformers. Then you can have sentence-level transformers. If this is not enough, you can do, for example, then paragraph-level transformers, and so on and so forth. And to reduce the number of parameters, we use weight sharing in each of this layer. And basically, that's it. Okay, so what was our motivation to start working on such problems? So, of course, deep learning works well when you have lots of labeled data. But unfortunately, the life is a bit more complicated, and very often when we start a new project, the first phase of the project is just a proof of concept phase where your client wants to do a very, very short project that just to check whether you are capable to solve this particular problem and just to get also the lower bound for the performance that you can achieve. And usually, for such POC projects, the clients don't want to put much effort and they don't want to invest much money for helping us with, for example, preparing the data. And of course, there are two problems. Labeling is expensive and often requires domain knowledge. And the other problem is that because of some legal issues, the documents that we are getting very often need to be anonymized. And actually, anonymization is even more expensive than labeling. And this causes that usually you end up with a small amount of labeled data. And I will show you two examples of the real projects that we did at Alpha Moon. The first one was aimed to extract useful information from notarial deeds. And this is basically just named entity recognition problem. And the case there was that the documents needed to be anonymized before we got them. So finally, we ended up with less than 50 documents for proof of concept phase. But still, we were able to achieve something around 0.75 F-score here, using some of the techniques that Szymon will show you in a while. And this is another example. The goal here was to classify reason for complaints, and this is just standard text classification problem. There was over 250 classes to recognize. We got a lot of unlabeled data, but only a couple of examples per each class that was labeled. And also using some techniques to combine unlabeled and labeled data, we were able to achieve over 0.9 macro F-score here. Okay, and this is the end of my part, and now Szymon will show you the rest.
So hi, my name is Szymon, and I will show you some approaches, some results we used, amongst others, in those two projects. So I will be dealing with a classification problem, and I will show you 4 basic approaches you could use to train your supervised classification model. So first one is classic supervised learning. So basic classification problem where you have big amount of trained data, labeled trained data, and you use standard techniques to train your model. Second approach, few-shot learning, where you have similar situation, but amount of trained data is very, very small. Next, semi-supervised learning, where you also have small train set, but you could support your training with some amount of unlabeled data. And last but not least, transfer learning, where you could train some big model on data that is similar to your problem, and then just use the knowledge you acquire to fine-tune your model also on small, possibly small trained data in your target domain. And this shows basically the history of our approach. So we started with supervised learning and went through all these stages while solving such problems. So first of all, some baselines. We started with supervised training, and our task was to classify the document. So document could have from 1 to like 50 pages of text. In our problems, we selected 2 data sets, so routers with 10 classes and 20 news groups with 20 classes. And we considered 2 baseline methods. So first, the baseline model was built from fast text embeddings for every token, and then averaged across entire document. And then for such average embedding, we built simple logistic regression and did the classification as per usual. And second baseline approach was to use deep learning model. So again, we used fast text embeddings, but this time we used the hierarchical transformer that was mentioned a few slides ago. And here are our baseline results. So for both data sets, you have F-score, so basically the performance of your model. And here you have amount of documents per class in your train set. So in both cases, you can see that simple model like logistic regression performs way better than a big model such as transformer or hierarchical transformer. But notice that at some point, transformer takes over. So as the amount of the trained data you have available increases, the performance of your model also increases. And those 2 plots will be shown on next slides, so you can compare our results against the baselines. So first interesting approach for such problems is few-shot learning. In this case, we used relational network. And authors of original paper, in this case, used images as input, so you have images here. This model consists of two modules. First module is called embedding module. And this part is responsible for embedding your inputs. So taking a latent representation of your input, whatever it is. And then second part, relation module, basically it takes concatenation of 2 inputs and tries to decide whether they come from the same class or not. And in our case, for embedding module, we used our hierarchical transformer as before. And for relation module, we used simple MLP. And the procedure is as follows. You take 2 observations from your data set, take latent representation using your embedding module, take a concatenation of both, and simply put it through your relation module. In our case is MLP. And then you have score for such pair you can later use in your loss function. So here are the results. So you have 2 baseline as before in blue and green. And in orange you have performance of such few-shot model, such few-shot learning approach. And notice that as for very small amount of data, even if you use, this is for transformer only, even for small amount of data, you can see that the performance of your transformer increased significantly. And in some cases, it even overcomes the simple logistic regression. But for us, it still wasn't enough. We still wanted to improve it way more because we believed that such powerful model can perform way better than simple logistic regression. So next step we took was semi-supervised training. And for this, we have 2 approaches. First one is called pi model. The basic idea here is that if you have the same observation, the latent representation for such observation should be the same or almost the same, even if you change the observation slightly. So even if you remove some words from your document, some sentences, the general class should remain the same. And to take this approach, we introduced additional function. In this slide is called G, and this is basically domain-aware perturbation of your input data. What it means, depending on what data you are using in your problem, this function should change to include the semantics in your perturbation. In our case, we deal with documents, so it was removal of words or removal of sentences from this document. For images, it could be some transformation on images. And we followed a pipeline proposed by authors. So we took observation X, we put it through stochastic augmentation, so basically it's function G. We took latent representation using network with dropout, so basically a hierarchical transformer, which includes dropout. And then you have two components. First component is cross entropy, so it's classic classification loss function. And then you have additional component, squared difference of those two latent representation. And what you want to achieve, even if you take the same observation and put it through stochastic augmentation, take latent representation, and the difference between both should be relatively small. You want to minimize the difference. And this loss component can be also weighted. In this case, the weight in original paper weight changed over time. And in our approach, we also slowly increased it during the training. And in second approach, we used entropy minimization in loss function. The general idea is to force model to make strong predictions. So we want to discourage model from taking relatively low probability predictions. We want to force the model to make strong prediction. And for this, we minimize the entropy over last layers, so over softmax probabilities. So entropy is minimized when single probability is high, and entropy is high if all probabilities are the same. And this component was also weighted by some parameter, and we also in our experiments used such parameter. So those are two approaches we used in our experiments, but there are also some honorable mentions if you want to read more about semi-supervised methods. Virtual adversarial training, mean teacher or pseudo labeling are the topics you want to read about. So as for the results, first we also, of course, took logistic regression, and you can see that the results are not very exciting. So logistic regression benefits very little from additional unlabeled data, even if we force a model to make have similar representations for inputs, for perturbed inputs, and force model to make strong prediction. Such tweaks make very little difference for such model. But in case of transformer actually has the capacity to incorporate more data, and as you use some unlabeled data, such information can also be processed and included in your modeling. And you can see that semi-supervised training improves the performance by considerable margin, especially this green plot. It's semi-supervised pi model transformer. So generally, such model trained in such way performs way better, but there is still some underperformance in very low, very small data sets. And we wanted to address this problem. So our approach we used in our solutions, in our experiments, was to connect relational networks, so the semi-supervised approach, with the few-shot learning approach with semi-supervised additional components in your loss function. So we took all three approaches, put it in one model, and trained it that way. So you have three components. First is supervised relational score. So as before, you take two observations, take latent representation, make concatenation, and then calculate the score using MLP. So this is the few-shot learning part. For second part, you take the same observation twice, but used function G in between to make slightly different latent representation, make concatenation and classify it. And you basically know that the same observation comes from the same class, so you don't really need a label for this. You know that the same observation comes from the same class, so this should be as close to 1. And we also included the entropy minimization technique in our later experiments. So what are the takeaways here if you want to actually use it in practice? Notice that weighting component, so the component in loss function, is actually mandatory. If you don't use it, your model will collapse very quickly and you will not achieve any results, basically. The training is pretty slow, so unfortunately, even if you have small data sets, like 20 observations per class, it can take like 3 days to train such model. And adding that last component, so entropy-based minimization, is actually quite tricky to approach in practice, but it's of course possible. So here are our final results for our approaches. In green, you have the fully mixed model with every tweaks we came up with. And as you can see, it generally performs way better than baseline transformer. It performs better than baseline logistic regression. And finally, even on small amounts of data, it performs better than any approach we could find and apply here. And finally, the transfer learning. We also tried to include transfer learning in our approaches. So transfer learning consists of 2 steps. First step is self-supervised language model training. So you have big model, you have a large amount of training data, and you can train your model on different data but lying in the same domain. And this step usually takes quite a long time, and currently such model is not available for every language. And second step, you take your pre-trained model, you take your trained data, and basically fine-tune this big model just to your small training data set. And this step is usually quite short. It can be counted in minutes. So performance of this model is shown here in red. And as you can see, such model performs quite good all across the board, but still, even if you take simpler models, so for example, transformer, such tricks, if you apply them correctly and you spend some time on tweaking your model where it's weaker, it starts to perform better at some times. And also notice that such approach actually requires you to have a pre-trained BERT model, which, as mentioned, is not always available. And as cherry on top, we actually did such BERT training on our side. So we used original paper and followed the original methodology for such training. We collected data from Wikipedia and open source ebooks, totaling around 4 gigabytes of text. And we also had to use some tricks to actually improve it for Polish language. One of those tricks was reverse order tokenization. So it wasn't done from the start of the word to the end, but actually backwards. And our final results, we achieved 0.78 language model accuracy. Language model accuracy is basically accuracy of prediction of missing words in your sentence. And 0.81 next sentence accuracy, so predicting whether next sentence was actually next sentence in your text or not, so basically context prediction. And to put it in action, we tried using our model in this year's PolEval competition. In task 6, it was automatic cyberbullying detection. And we achieved f-score of 56.17, which would put us on third place in final leaderboard. So as for the conclusions, semi-supervised learning can easily boost your model's performance, even if you have small amount of, especially if you have small amount of data. And few-shot learning, in our case with relational networks, can be easily boosted further with semi-supervised techniques. And lastly, while transfer learning may be easiest way to go and most tempting way to go to start with, you should know that if you have small, few labeled data problems, such small tweaks, as mentioned, can actually give you way better results. So thank you for listening. If you have any questions, now would be the best time.